Hello everyone and welcome again to a new lecture, and we are going to continue as quickly as possible from where we had left our discussions. We were doing the discussion on the transformation or the building a relation between the scattering angle in the lab frame and then in the center of mass frame of reference. So we did some calculations. I hope I have reached to some conclusion. So this is what we had. So we had come across two relationship. This if you say this two relationship between this lab frame and scattering angle, and this is the center of mass at scattering angle. So we have two relation. One is in terms of the cos theta, and this is in terms of the tan theta, and this is another quantity which is related to this rho, and which depends upon this v0 and v1 prime. This v0 is the relative velocity of the particle 1, which is the projectile in case of the fixed target or lab system, and after the collision, and this is in the center of mass after the collision frame of reference. And this on the left hand side, all these are in terms of angle is in terms of the center of mass. Here also angle is in terms of the center of mass on the right hand side, sorry, and on the left hand side the angle is in terms of the lab frame. So to get rid of this this v1 prime, this is v naught is the relative velocity of the particle 1 after the collision in lab frame, and this v1 prime is the relative velocity of the particle 1 in the center of mass frame. So if we know the relation that how this position coordinates are related in when you deal in terms of the center of mass coordinate system. So from there we can have the velocity, this v1 prime, this v1 prime is related to v. Okay, so that I'm going to replace this v1 prime here in this expression to this v. So that's we get this m1 upon m2 and v upon v. Then okay, we had already discussed this, that in case of the elastic scattering, this elastic scattering, the total kinetic energy two particles remains unaltered. So this v0 and v1 is going to be 1, and so the rho is going to give me the ratio of the mass, the projectile, and this target. Okay, and the second thing is that if the target is very high in case of related to m1, so this m1 by m2, this ratio m1 by m2 is going to be approximately equal to 0 because the denominator is very large. So then in this case the scattering is going to be same either in the lab system or in the center of mass frame of reference. So scattering angle is going to be same, that is for the Fish scattering center. Now moving further for this inelastic scattering, because these were for the elastic scattering, but in case of inelastic scattering, we know that the total kinetic energy of the two particles is altered. That is, the sum of the kinetic energy goes into some other forms of internal excitation energy of the target or some other type of things that comes into play. So that the main thing is that kinetic energy of the two particles is not going to be same as in case of the elastic scattering. So since the total energy is conserved and the momentum is also going to be conserved in every reactions scattering, the energy change resulting from the collision, so this is going to be before this is a half mu v square, because mu is reduced mass of particle 1 and 2. So kinetic energy plus this some resulting collision. So q is going to be certainly is going to be the negative, because the energy is getting rid of the system, coming loss of the energy from the system. So but q is certainly is going to be the negative. So from this relation we can have one this ratio of v square and v naught square. So this is going to be 1 plus this is, if you take the ratio of these two, so going to be 1 plus twice q by mu v naught square. And then if I write mu as m1 m2 upon m1 plus m2, so this is what I'm going to get is so I can figure it out that this is 1 plus m1 m2. If I take m1 this side, m1 from here to here, so this is one mathematical notation. So this is for some reason, because if I take the square of this goes under root, and this quantity, this is, if you see, this is or say this quantity 2, this is twice by m1 v naught square is nothing but so if you remember that this is, if you write energy is kinetic energy is half m1 v naught square. So if you divide, this is going to be twice of this is going to be the energy, inverse of the energy. Okay, so this is being replaced here. So in this here, that's why this 1 from here is transferred here, so to make it in terms of the energy of the particle. So this is going to give me this loss of the energy. So because the kinetic energy of the incoming particle is the lab system is this v naught in the lab system is there, half m naught v square. So for inelastic scattering, this rho, which was this is if no, rho is my m1 by m2, and this is v upon v naught. If you remember, this is v upon v naught. So this is v upon v naught. Okay, so this is, so v and v naught, we have got relation here. This is going to be m1 upon m2, and because this is inverse of this. Okay, that is v naught upon v, and this is v upon v naught. So this is v naught upon v is this is v naught upon v. Okay, v naught upon v. So that's why this is in the denominator. This quantity is in the denominator. Okay, so this is also a very important relation which we are going to use after some time. The rho in terms of the, now we get rid of the velocity. What is there is earlier it was in terms of the velocity, and now it is in terms of the energy. This is the loss in the energy, and this is the energy of the particle. Okay. So now, so not only the scattering, this I think so now we can find the second important thing, that not only the scattering angle, this in lab system, this is in lab system, this one, and this is in this, the center of mass is different in magnitude. Okay, in general, you see the scattering in the lab frame and in scattering in the center of mass frame is generally is different in magnitude. But if you do the experiment and calculate this differential scattering cross section, because you write differential scattering cross section in terms of in differential scattering cross section in center of mass frame of reference here and the lab frame of reference here, so they are either also going to be same in that case. But there is one catch, that we from there we can get the connection between the two functional form is obtained from the observation, that whatever lab frame you do your experiment, you perform your experiment, the particle scattering into a given solid angle must be the same, whether we measure in a lab system or in the frame system. So that is going to be same. Okay, so the natural scattering is not going to be different in, like, if the frame is just in what frame you are measuring. Okay, it depends upon the flux, what the observer is seeing, but the total scattering is going to be same, whatever this. So that on the basis of this, what I'm going to say, that this is that because this is going to be same, the number of particles scattered along this element d omega of scattering is going to be same. So that is, if you recall, that is going to be twice pi, and this is going to be the intensity, and this is twice pi sine theta d theta comes from this d omega. So this is kind of d omega, I omega, d omega kind of thing. So here, or in the center, in the center of mass frame, or in the lab frame. Okay, in the lab frame, this is to be prime for. So if I establish the relation between the lab frame of reference, differential scattering cross section in the laboratory system, and the differential scattering cross section in the center of mass frame of system, that is it is related with this sine theta angle and this d theta by d omega. So d theta sin theta, this d theta sin theta is d of cos theta, and sin theta d theta, this is also going to be cos theta. This is in center of mass frame, this is in the lab frame. So because we had relation of cos theta, we have relation of cos theta here. So we have relation of cos theta in lab frame and center of mass frame. From this relation, from we can calculate this quantity. Okay, so this quantity we can calculate, so that we can establish relation between this cross sections, differential cross section in lab system and the center of mass system. Okay. So this can be easily, so this is my relation, this is cos theta, which in lab scattering angle, and this is in center of mass scattering angle. So we had to find this d cos theta and d of cos theta here. So because this is d cos theta, so what I'm going to get is so this is what we have to integrate, okay, with respect to d cos theta. So I have cos theta here and I have cos theta here. So if I fix this is, say this is my u, and okay, so I say this is my u, and this is my v. So I'm going to get is d of cos theta as u and 1 by v. So what I'm going to get is taking one of v constant, d and d of cos theta of u, and plus u constant, d and d cos theta of 1 by v. This is what we will get is, so this is 1 by v, this is 1 by, this is my v, so this is constant, and then u is this rho cos theta. So this is, we are differentiating with respect to the cos theta, d cos theta. So this is cos theta is going to be 1 here, and then I have plus here, so this is going to be plus, or minus will get from here. So then this is u is constant, so this is, I'm going to get this u is constant, rho cos theta is constant here, rho plus cos theta is constant, and then I have to integrate this. So this is going to be d cos theta of this is 1 plus 2 rho cos theta plus rho square, this is minus half. So what I'm going to get is, this is there, this is rho plus cos theta, and this is going to be minus half 1 plus 2 rho cos theta plus rho square minus 3 by 2, and then this, because I'm differentiating with respect to cos theta, so this is going to be twice rho. Okay, so this 2 will cancel out, and this minus make this plus is negative, and then I have minus 3 by 2 is, and then I left with rho. So rho multiplied by this rho is going to give me the rho square, rho multiplied by this cos theta is going to give me the rho cos theta. Okay. So now we have this plus this, so and then if you take the LCM of this thing, so this here it's you're going to get 1 plus 2 cos theta. So in this place here you're going to get 1 plus 2 rho cos theta plus rho square, and then minus of this. Okay, then minus of this and minus of this. So this will cancel out, and then 2 rho cos theta minus rho cos theta is going to rho cos theta. Okay, and this one is there. So this is very straightforward, you get the calculation. So what is the relation you get is this d cos theta. So this we have figured out. So these quantities relating the differential scattering cross section between the two frame, okay, between the lab frame and between the center of mass frame. So this is what the quantity which is relating to differential cross section. So here you can note that the sigma theta, either you calculate the sigma theta or sigma theta, the function on which it is depending is the scattering in the center of mass frame or in the lab frame. But it's the both these things are being calculated. Sigma theta and sigma theta are the cross section measured in the laboratory system. Okay, so they are merely expressed in terms of the different coordinates. So this is what practically is useful. So then on the basis of this expression, we can discuss some conditions for, like in case of elastic collision. So we know that in case of elastic collision, that we have rho is m1 by m2. Okay, rho is m1 by m2. So then I can get if my target is very heavy. So in case of like if you see in case of Rutherford scattering, where you have helium particle of say m1 is 4, so m1 is 4, and this gold, if you take the gold, that is going to be have around 200 atomic AMU, then this m2 is very large as compared to m1, so this rho is going to be 0 from this relation. Okay, from this relation. So when m1 by rho is going to be 0, so if we put it here, this is my relation between the scattering cross section. If you put rho equal to 0 in this relation, so what I'm going to 0. So this is 0, this is 0, this is 0, and you just have 1. This is going to be rho prime theta is equal to rho. This is, so scattering is going to be same. Okay, so either differential scattering cross section is going to be same in case of elastic collision. Okay, when this target is very heavy as compared to the projectile. Now if this the second thing, if your m1 is approximately equal to m2, that means if you're doing this quantity is going to be 1, because m1 and m2 are practically equal. So this case of like you are doing the neutron proton scattering. So we have from the relation we have cos theta. So other relation we have cos theta, that is, if you remember that. So if this is going to be 1, this is going to be 1, this is going to be 1. So this is 1 plus cos theta, and then this is 1, this 1 plus 1 is going to be 2 if you take 2 common. So 2 1 plus this is 1 plus rho cos theta. Okay. So I can write this 1 plus cos theta, this 1 plus cos theta as 1 plus cos theta, and this is 1 plus cos theta. So 1 plus cos theta you get rid of in the denominator, and then you have this cos theta divided by 2. So this is nothing but cos squared theta by 2, this quantity. So this is, you are going to get cos theta by 2. So here you have cos theta and you have cos theta by 2. So the two angles are related with this, the center of mass angle and this lab frame. So here the one condition is that if in elastic collision you are doing scattering with the projectile and target particle, which are of equal masses, then this scattering angle in the center of mass frame and the relation between the lab frame is going to be theta by 2. So that means whatever the scattering angle is in center of mass frame, the lab frame is going to be have the half of this. So this important relation sets one condition that with equal masses, scattering angle greater than theta 90 degree, that is, this theta is in the lab frame, theta 90 degree cannot occur in the laboratory system, and all the scattering is in the formed sphere. So that means if the particle in the same target is here, if the particle is coming, this cannot happen. Thus only this scatter, if the particle is coming and this much of, not more than from the initial direction, this is going to be 90 degree, and this is my theta in the lab frame. So more than this scattering is not possible. Okay, more than this scattering is not possible in case of the lab frame. Okay, because there will be energy log constraint will be. So if this is if you put this condition there, then this projectile is totally going to lose its energy, and then this is going to get absorbed in the target. That is for equal masses only. If the scattering is with equal masses, not with all these. Because like if it is more than 90 degree in lab system, then you say this is going to be the theta 2 is going to be negative. Basically, if this particle is going to be going to have scattering on this, then this is going to have negative scattering in negative angle in the scattering direction. So this is one reason that that if a particle is coming and it's going like this, okay, then if it's scattered, then this is okay. But when this is more than this angle is going to be, for this theta 2 particle, is going to be negative. So then for that reason this lab scattering angle cannot be more than 90 degree. And then we will see further that there is energy constant loss is also there for equal mass scattering possible, not for all the conditions. Okay, so this you have to remind that this is for equal masses. This is important. And the second thing is corresponding to scattering cross section, and in terms of theta I can write this is that is, if m1 equal to m2, then what we have, rho equal to 1. So this is again, this is in terms of the scattering angle, that if you have equal masses, rho is 1, then this scattering angle in lab frame cannot be greater than 90 degree. But if you see the scattering cross section, then the sigma prime and sigma theta, these are related with this. So if we put rho is equal to 1, rho equal to 1 here, so this is again 1 plus 1, 1 plus 1 is going to 2, you take 2 constant, this is 1 plus, this is cos theta, we know the relation, this is going to be theta by 2, so this is going to be 2 theta. So I can write this center of mass angle as 2 times the center of lab frame angle. So whatever the center of mass angle is here, so I am going to write it 2 times this in the lab frame. So here also this is going to be 2 times. So this is 1 plus cos theta, 1 plus cos 2 theta. Okay. So now this is 3 by 2 and this is 1. So this is, if you take minus 1, this is going to be half here. Okay. And then this is cos 2 theta. Cos 2 theta I can write is 1 minus 2 sin squared theta. And then this is going to be this is 1 plus 1 2, so I am going to have 2 common, 1 minus this is sin square theta under root. Okay, so this is under root, so 1 minus sin square theta is cos square theta, and then you have this cos theta, and then this is 2 with 2 to the power 1 by 2 and 2 to the power 3 by 2 is going to be have 3 by 2 plus half is going to be have 2. So 2 to the power 2 is going to be 4, and this sigma theta and sigma theta. Okay. So now what we have is the relation between this is the differential scattering cross section in the lab is going to be 4 times this cos of theta in terms of this center of mass differential cross section. Okay, where the condition is that this scattering angle has to be less than equal to, cannot be greater than 90 degree, and rho is 1. This is for equal masses. So one is here that for equal masses in elastic collision, the scattering angle in lab system cannot be greater than 90 degree, and the second relationship is this sigma prime theta is basically so this has to be theta, this has to be theta. Okay, because now we have 1 minus sin square theta, this is going to be this. So, and second is this relation. So we've seen that even in elastic collision also, that when you have a projectile coming and this is my target, so if it is getting scattered, and because of the recoil this particle also gets scattered into this. So this is the total kinetic energy remains constant even in elastic collision. A collision with initially a stationary target is there is a transfer of kinetic energy to the target with a corresponding decrease in the kinetic energy of the incident particle when this happens. Okay, so in other words, the collision slows down the incident particle. So that means that if the collision is happening, so this whether it is elastic, this collision is there is energy loss, okay, of this incoming particle. So that can be seen from this relation, that we can prove this, that if I have one relation is center of mass velocity and this v naught, and these are the relations we have already calculated, and this is one, if you remember. So here in this relation, if I do in place of v, I replace this is mu square m naught square v square, and this v1 square is this in terms of this mu square rho m square V, and then I have twice V1 and V, and this is cos theta. Okay, this is in center of mass frame of reference. So now I have is I have this I can get common mu upon this is this I'm getting common mu upon rho m naught square is very common. So this becomes, this is V1 and V0 I can take outside here, and then so I've take common here, so this becomes 1, and then with this I becomes, this is 2, and cos theta is there, and this there is if I multiply it by this rho, so this becomes a square. So this is why this rho is here, and then for this I have to have by divided by rho square, so get this rho square. So for now elastic collision, I know this is m1 by m2 because rho is m1 by m2, this is v0 by v, so this is going to be same equal to elastic collision, this is 1, so this is going to be, rho is going to be m1 by m2, this is going to be 1. So if you concentrate on this this mu upon rho m2 square, this mu is m1 m2 by m1 plus m2, and this is 1, and rho is if I write m1 by m2, and this is my m2. So what I'm going to get is like m2 will cancel out, okay, and this m1 is also cancel out, so this m2 goes up, and this is a whole square. So from here if I take m2 common, so this is 1 plus m1 by m2, this is also getting common, so this is, and m1 by m2 is my rho for elastic scattering, so this is 1 upon 1 plus rho ka whole square. So this is going to be this quantity is going to be 1 upon 1 plus rho ka whole square. So so this v1 square upon v naught square is this quantity is 1 upon 1 plus rho whole square, and then you have 1 plus twice rho cos of this theta in center of mass, and this is rho square. So this is why what I have here. So then this can be related with the kinetic energy, because this is going to be half mv1 square or half mv0 square. This is the ratio of the kinetic energy E1 and E0 and E1. So this is E1 by E0, because E0 is the initial kinetic energy of the incident particle in the laboratory system, and E1 is the corresponding energy after the scattering. Okay, so what is the energy loss is going to have E1 by each ratio? So I have this is what we figure out, and is divided by 1 upon rho square. So when in the elastic scattering, you know that rho is going to be for m1 equal to m2 for equal mass particle, because for elastic scattering rho is m1 by m2, and for if m1 is approximately equal to m2, so this is for this is going to, this rho is going to be 1. So if you put rho is 1 here, rho is 1, so this is 1 plus 1 2. So this is going to be 2 square, and from here this is 1 plus 1, then go to 2, you take 2 common with this 2, and that will cancel by this 2 square. 4, 1 is you going to get 2 here. So and 1 plus cos theta is cos square theta by 2 divided by 2. So this is going to be cos square theta by 2, and this is nothing but, because this is in center of mass frame of reference, so this can be written in the lab system. So you see that the relation, that is E1 by E0 is going to be cos square the angle in the lab system, and this is energy. E1 is the energy of the particle 1 in after the collision and scattering, and E0 is the initial kinetic energy of the incident particle in the lab system for the scattering. So that is, this is related with this. So that means E1 is after this kinetic energy after scattering is going to be E0 times cos square, what is the scattering angle, theta. So thus if this theta is cannot be greater than pi by 2, so if you put pi by 2, theta is equal to pi by 2 maximum, this cos is 0. So that means the kinetic energy, this E1 after the scattering is going to be 0. That means it is completely getting absorbed inside stopped in the laboratory system in the target. okay. Or you, if you say this is theta equal to pi, so this is getting a stop in the target. So the kinetic energy after the scattering is going to be 0. But this is important in point of view, that is, this is for equal masses and elastic scattering. So this transfer of the kinetic energy is by this kind of elastic scattering for equal masses. This is the principle behind the moderator in the thermal neutron reactor, because in that fusion process, when the fast neutron produces in the fission, this fast neutron makes successive elastic scattering. So because this relation established that in elastic scattering there is a loss of there is going to be loss of kinetic energy, and at angle pi by 2 it is going to be completely a stop. All the energy is being absorbed by the target. So that is this, every elastic scattering is going to reduce the energy, and this is going to be reduce the thermal energy, where they are more liable to cause fusion than the captured. Okay, so clearly the base moderator will be the light elements. That means we have to put this rho equal to 1. This is m1 upon m2 has to be, this m1 is my neutron because this is fast neutron. So m2 has to be like ideally to be hydrogen, so that my rho get m1 by m2 equal to 1. So that this relation holds good, and then the scattering of this fast neutron is going to reduce the energy of the system. Okay, so I think this is done for today's lecture, uh, and this is also done for this topic, that to establish the relation between, or connection between, the lab frame of system scattering and the center of mass frame of system scattering. We have seen that the two relations, and seen that the scattering cross section, differential cross section relation between how it depends upon the scattering in the lab and the scattering angle into the center of mass frame system. And in case of the elastic and inelastic conditions, how depending upon the masses and the velocity, the two important conclusion is that in case of the equal mass scattering, or in case of elastic scattering, you have the lab scattering angle is going to be always less than equal to 90 degree, cannot be more than 90 degree. And second is that in there is kind of energy loss is there. So that is going to be used in very useful purpose. So with this remark, thank you very much, and I'm stopping this lecture right now. Let's hope to meet soon for the next lecture. So there we will start the new topic, that is the canonical transformations. Thank you.